In the last video, we defined the motion of a spring, and we defined it in terms of its distance from equilibrium, and we'll use the general formula x function of t is equal to some amplitude times the cosine of omega t plus phi. And we were looking at some constant k, and I'm going to use a subscript s because we're going to end up using k in about 3 different ways this semester. And in physics we always, I guess, like to reuse constants, so I'm going to try to put it in terms of a subscript. And this is called the spring constant. Remember, it's individual to a spring based on its material density and the how tight the windings are. A lot of different things go into it, but this K of the spring describes how the spring reacts to being stretched or compressed, and the units are in newtons per meter. We also had some mass attached, and we also had the mass moving, and there is a parameter omega that is based on the spring constant and the mass. Now, this is called angular frequency, and it's not to be confused with rotational angular velocity. Remember, when we talked about angular rotational velocity, we were looking at something that was spinning, and you had some rotation that had some omega related to that. That's not what we're talking about. Because we're dealing with a spring moving in a straight line, we call it angular frequency. We still use the definition of frequency in our discussion. We want to remember that for omega is equal to 2 pi times frequency, which means that frequency is 1 over 2 pi times omega, and omega is just the square root of k of the spring over the mass, and so now we have a formula for frequency, and the definition is fairly similar to what we had for frequency. It's basically how many round trips or how many complete trips occur in 1 second. Let me write this a little bit better here, space it out. And we have also the period, which is just 1 over the frequency, and that's just going to be 2 pi times the square root of the mass over the spring constant. And this follows the amount of time that one complete trip requires. So remember that this is frequency. Forgot to write this. And this is period. Now when we mention complete trips, what we're saying is, let's imagine, I'm not going to draw the spring, but let's imagine we have the mass sitting here and we have some point. So a complete trip would be the mass moving from this point out to its amplitude, then returning all the way over to the other amplitude, so we'll call it negative A, and then returning to the same spot that it started out from. That's how we would define a complete trip. One oscillation. Now, let's take the formula for the distance, x function of t equal to a cosine omega t plus phi. And let's take the derivative to get the velocity. So I'm going to have to use the chain rule, and that's going to be cosine, well, we have the constant a, cosine, its derivative is the negative of sine, then I have to take the derivative of what's inside, and that's just going to be omega. And I can also put this in terms of the spring constant and the mass, negative amplitude times the square root, k the spring over the mass, times the sine omega t plus phi. And so the max velocity is going to be equal to a times the square root k the spring over the mass. And we're always going to look at this, at this point we're going to just say it's positive. We know that depending on which side, it could be positive or negative if you use the vector, but we'll just talk about the positive for the moment. Now the acceleration is going to equal the derivative of the velocity, and that's going to equal the second derivative of the distance. Well, I already have the velocity here, so I'm going to have a negative a times omega. Omega is a constant, remember. And now I can do my derivative of the sine, which is the cosine. And then by chain rule, I need to take the derivative of what's in here, and that's just going to be omega. And we can substitute in for omega. And our max acceleration is going to be a times k of the spring over the mass. Now let's see the relationship of this in this simulation. You notice it shows you the acceleration vector, and the acceleration vector is going to point towards the origin at this point, or the equilibrium point. And you'll also see the velocity vector in red. And I want you to notice the relationships between the velocity vector and the acceleration vector. So let me start the simulation. And you notice that here the green is the distance away from the equilibrium point. So the equilibrium point is here at 0. The velocity, when the x function is at its peak, the velocity is 0, and then it reaches its peak at a point here where the mass is moving through the center line. And then the velocity is 0 when the mass has achieved its maximum amplitude in the opposite direction. And then the velocity is a max when the object goes through the equilibrium going in the opposite direction. So when you look at the vector for the velocity, let me reset this, you notice that the velocity vector always points towards the ends. Once the mass gets to its peak, then the velocity vector instantly changes directions, but it always points to the ends until the mass gets to that, and then it flips direction. Now let's look at the acceleration in terms of the distance formula. So you notice that the acceleration is a maximum when the object is in its maximum position at the amplitude, and the acceleration is in the opposite direction of the mass. When you get to the object being at the equilibrium point, there is no acceleration because there is no force of the spring. The spring's in equilibrium. And if there's no force, there's no acceleration. And then as the mass gets to the opposite extreme point, the acceleration is now pointing in the opposite direction. Now look at the acceleration vector as we run the simulation. And you'll notice that the acceleration vector always points to the equilibrium. Depending on which side the mass is, it'll always point to the equilibrium. So let's watch that now. There it flips back. See how the mass moves across the equilibrium and the acceleration vector changes direction to always point towards the center. These are some of the properties of springs, and these are how we quantify these properties using the mass that's attached to the spring and the spring constant. That's really all we need to understand. We notice that the amplitude does not have anything to do with changing the frequency of the spring system. So the amplitude could be shorter, longer. It doesn't really matter. The only thing that we need to change the frequency is the mass and the constant of the spring.